Hello and welcome to today's revision session where we're going to look at capacitance in AQA A-level physics. So in today's lesson we're going to review the concepts of capacitance. So the first thing we're going to look at is an introduction to this idea of capacitance. Now capacitors are electrical components which can be used to store electrical charge in a circuit, and they come in many different shapes and sizes. Now on the screen you can see examples of capacitors found in the real world. Now a capacitor can store electrical energy when it's connected to a charging circuit, and when it's disconnected from its charging circuit it can dissipate that stored energy. Now capacitors can be used as a temporary battery, and capacitors are commonly used in electronic devices to maintain a power supply whilst batteries are being changed, as it prevents the loss of information and volatile memory. Now since capacitors only store small amounts of charge at once but can discharge this charge very quickly, this makes them very useful in situations where a quick burst of charge is needed. So for example in a defibrillator, for example in a camera flash, for example in an ignition switch of a car, for example as an emergency backup for an electronic device. Okay, all these examples need a small amount of charge but delivered in a quick burst. Now it's important to note that we need to understand what a capacitor is, how it works, and how we can quantify a capacitor. So capacitance of an object is a measure of the amount of charge stored in an object per potential difference used to store it. Now this definition comes from the idea that the electrical field produced by a potential difference can be used to store an electrical charge, and we can use this definition to find an equation for the capacitance. So capacitance is equal to charge stored in the capacitor divided by the potential difference across the capacitor. Now we have our units of charge to be coulombs, our units of potential difference to be volts, so therefore our units of capacitance are coulombs per volt, and we can also give this a name of a farad. So 1 farad is 1 coulomb per volt, and this is named after Michael Faraday, who was the first scientist to develop capacitors effective enough for practical applications and to measure the effect of different variables on their capacitance. So this means that a capacitance of 1 farad is when 1 coulomb of charge is stored due to a potential difference of 1 volt being applied across a capacitor. So for example, a capacitance of 20 farads will mean that 20 coulombs of charge will be stored for every 1 volt of potential difference placed across a capacitor. A capacitance of 40 farads will mean that you have 40 coulombs of charge stored for every 1 volt of potential difference across the capacitor. Now we can assume for a capacitor that the capacitance of a capacitor remains unchanged throughout its use. Now in reality a charge will leak in a capacitor over time and the capacitance will change, but for A-level AQA physics we only consider the minimum capacitance of a capacitor, which occurs when the potential difference is a maximum, and we consider this to be an unchanging value. Now just remember, in this equation the potential difference is the potential difference across the capacitor, not across the entire circuit. So be mindful of this when answering questions when you've got to consider the potential difference of a branch or of an entire circuit. Now the charge in this equation is the charge of the capacitor. However, charge cannot be created or destroyed, so this charge, as well as being the charge of the capacitor, will also be the charge of the circuit as the capacitor is charging or discharging. Now this charge calculated in this equation can be used to calculate the current flow of a circuit. Now please note the farad itself is a large unit because individual electrons have charges on the order 10 to the minus 19. So it's more common to see capacitance expressed in terms of microfarads, nanofarads or picofarads. Now interestingly, batteries store charges on the order of about 1,000 or 6,000 farads because they don't use the electrical field to store their energy, they use chemical means. Now because they store energy via chemical means as opposed to the electrical field, a battery can store much more energy than a capacitor, but it finds it a lot harder to convert the energy into other forms compared to the capacitor. Now a capacitor which stores electrical charge consists normally of 2 conducting parallel plates separated by a gap. Now these parallel plates will produce a uniform electrical field between them. Now we show that the capacitor is made from 2 parallel plates with a gap in between them with our circuit symbol for a capacitor. Now when the capacitor is placed into a direct current source, charge will build up on its plates. So the plate connected to the negative terminal of the power supply gains electrons, it makes it negatively charged, so that's an important idea, and the plate connected to the positive terminal loses electrons and makes it positively charged. So what happens is the electrons on that positively charged plate are attracted to the positive terminal and are repelled by that negatively charged plate. Now, it's important to note that the electrons will leave one plate to become positively charged and go on to another plate to become negatively charged. Now, this will only happen if the current which flows through the capacitor is a direct current, not an alternating current. So what happens is, over time, once charge builds up on the plate, a potential difference is formed between the plates. So this means that a charged object would have to do work to move between the plates, as there's a potential difference. Now, in between these two plates is an air gap. Now, that's important because the electrons from the negatively charged plate cannot travel across the air gap to the positively charged plate, even though there's attraction, because air is a poor conductor. So the better the insulator between the plates, the greater the charge imbalance that can form. So because there's a gap between the two plates which prevents the electrons from moving between the plates, that creates a charge imbalance over the two plates. Now, this effect can be increased if we fill the space between the plates with a material which is a worse conductor than air. Now, these types of materials are called dielectrics. So your dielectric must be a better insulator than the air or a vacuum. Now, what happens is, if we have a potential difference across the two plates, it means the capacitor can store charge on its plate which it can later discharge, and this is how the capacitor stores electrical charge. Now, what happens is, because you have two parallel plates with a potential difference between them, there's a uniform electrical field between these two plates. Now, technically, no extra charge is stored on a capacitor when it is charged compared to when it's uncharged, because what has happened is on the negative plate it has gained electrons, and on the positive plate it has lost electrons, and it is the same amount that has been gained by the negative that has been lost by the positive. So it's important to note that overall the number of electrons on your capacitor has not changed. So the capacitor overall remains electrically neutral. However, this movement of charged particles creates a potential difference across the plates, which produces a uniform field between the plates. So what this means is, any charged particle in the dielectric medium will experience a force and become an electrical potential energy store. So you've got your electrical potential energy stores. So technically, a capacitor actually stores electrical potential energy produced by an imbalance of charge in its plates interact with the medium between the plates. However, this energy is released in the form of moving charge, so it appears to be storing charge rather it's actually moving charge that's already present. Now, it could be argued that the negatively charged plate stores charge, but overall the capacitor does not store charge. Now, it's again important to note that our capacitor stores electrical potential energy in the dielectric, and this energy can then be released in the circuit in the form of moving electrons when it is discharged. Now, this process means a little energy can be stored in a capacitor compared to a battery, but it can be released very quickly. So it's important to note that when a capacitor is discharged, the current in the circuit goes up as there are more electrons flowing, but the potential difference across the capacitor decreases as less potential energy is stored in the dielectric. Now, let's consider our parallel plate capacitors. So as we mentioned before, a capacitor consists of two conducting plates separated by a gap, and this charge imbalance on the plate produces a uniform electrical field between them. Now, it's important to know that, like we said before, the charge on either plate must be the same magnitude but in opposite signs. So if one was plus 10 microcoulombs, the other will be minus 10 microcoulombs. Now, to maintain this attraction, electrons cannot travel from the negative plate to the positive plates, so the two plates, like we mentioned, are separated by an insulator. Now, again, it's important that if the insulator between the plates is air or a vacuum, we state the charge stored by the capacitor to be Q0. The capacitance to be C0, which is an important idea. Now, we can increase the capacitance or charge stored of the two plates by placing a greater insulator between the plates, because there's even a smaller chance of electrons travelling between the plates. Now, this type of material is called a dielectric. Now, it's important to note, okay, that if the electrons do travel across the dielectric from plate to plate, we say the dielectric is broken down, the capacitor can no longer store charge. Now, examples of dielectric materials include wax paper and polythene. Now, the increased capacitance of a capacitor after a dielectric material is inserted between the two plates is given as C, and the increased charge of the capacitor after a dielectric material is inserted is given as Q. Now, the effect of adding a dielectric material to a capacitor is called the relative permittivity. Now, the permittivity is a measure of how difficult it is to generate a uniform electrical field in a certain material. So the important thing to note is the permittivity of free free space is how difficult it is for a vacuum or air to generate a uniform electrical field, which is a physical constant in our universe, which equals 8.85 times 10 to the minus 12 farads per meter. Now, the relative permittivity is a measure of how good a material is to generate an electrical field compared to how well free space generates an electrical field. So we can calculate relative permittivity with the equation of Q over Q0, C over C0, or E over E0. Now, in all the cases, this value has no units as a comparison showing the effect of the dielectric. Now, another name for the relative permittivity is the dielectric constant. Now, it's important to note that the higher the relative permittivity or the higher the dielectric constant, the better the insulator the dielectric is. Now, we've got to think to ourselves, how can we alter the dimension of the capacitor to increase the electrical potential energy stored in our capacitor? So what can we actually do? Well, the mechanism by how a capacitor works is it works due to the attraction between the two plates caused by the charge imbalance, but making an electrical field which will store electrical potential energy in the capacitor. Now, any way to increase the attraction between the plates increases the electrical potential energy stored. So this includes decreasing the plate separation, making the area of the plates as large as possible, and filling the space in between the plates with a very strong insulator, which will increase the energy stored in a capacitor. So a capacitor stores electrical potential energy as the potential difference between the plates which causes an attraction between the plates. The greater the attraction, the more energy that can be stored by the capacitor. So to do this is only true when the electrons cannot move between the plates. So you can increase the attraction between the plates by increasing the areas of the plates, as allows more charge to be stored, decreasing the space between the plates as allows a greater interaction between the two plates, and increasing the dielectric constant of the material. The greater the insulation, the less likely it is that the charge will travel between the two plates, which we can express mathematically with our equation capacitance is equal to area times by E0 ER over D, where A is the area of the plates in meters squared, D is the distance between the plates in meters, and ER is the relative permittivity. But we can only use this equation for a parallel plate capacitor. So this equation tells us the surface area of the plate and the capacitance are directly proportional. It also tells us the distance between the plates and the capacitance is inversely proportional. Now, it's also important to note that our dielectric, as well as being a very good insulator, should also be polarized, as this increases the dielectric constant. Now, it's important to know that a polarized molecule contains areas of positive and negative charge in its structure. Now, when a capacitor is unpolarized, it has no charge placed upon it, the polar molecules of the capacitor move in random directions. So when the capacitor is unpolarized, the polar molecules are randomly orientated. However, when a capacitor is charged, it produces an electrical field across the two plates. This means the polar molecules rotate to attract the opposite charges. So it's important that the polar molecules align with the oppositely charged plate as the opposite charges attract each other. So this will produce an electrical field in the opposite direction to the capacitor. Look at the alignments of the charges to observe this. So because the polar molecules have rotated anti-parallel to the electrical field of the capacitor, there's the two electrical fields in opposite directions, reducing the overall electrical field. And so the electrical field is produced on each plate. Means the greater the electrical field, the harder it is to place more charge on the plate. So because we've reduced the electrical field overall, this means that it's important to note that this process can force further electron movement found in the charging process. So you can consider it that the negative side of the dielectric pushes the electrons back to the battery from the positive plate, making them more positive, and the positive side of the dielectric attracts more electrons from the battery onto the negative plate, allowing more charge to be stored, increasing the capacitance. Now let's consider charging and discharging capacitors. So a capacitor will charge when it's connected to a positive and negative terminal in a complete circuit, so a battery or a power pack. So a positive plate forms where electrons are removed from the plate, and negative plate forms where electrons are added to the plate. Now, when the plate connected to the negative terminal gains electrons, it makes it negatively charged. Now this occurs as the negative terminal repels the negative electrons onto the plate. Now this occurs as the negative terminal will push the electrons onto the plate, and this will happen quickly at first as there's no charge on the plate, so the electrons freely move onto the plate. But over time the charge builds up, so it makes it more difficult to place more charge on the plate as the electrons repel the additional more electrons onto the plate, so the rate of charging slows down with respect to time. And it's the same idea for the positively charged plate, except it's the idea of the electrons leaving the plate as opposed to going onto the plate. But the effect occurs quickly at first because there are many electrons on the upper plate, but over time, because a positive charge builds up on the plate, it makes it more difficult to move the negative charge off the plate, so the rate of charging slows with respect to time. Now, in our idea of charging, the electron movement is always towards the positive terminal. Now, it's important to note that when the capacitor is connected to the direct current source, this will cause your potential difference to form between the two plates, and we can measure the rate of charging by measuring the potential difference across the capacitor. But what happens when it discharges? So when you have a charged capacitor, there's a potential difference between the two plates. So there are fewer electrons on the positively charged plate and more electrons on the negatively charged plate. Now this particular charge imbalance is held in place by the positive and negative terminals, because the negative terminal is repelling electrons onto the negative plate and the positive terminal is attracting electrons off the positive plate. So this imbalance is only held because of those terminals. So to discharge a capacitor, we remove the terminals, we turn off the EMF of the circuit, because when this happens, the charge imbalance no longer holds. So the electrons on the negative plate repel each other, so there's now no repulsion from the negative terminal pushing them off the plate. So the electrons will stream back off the plate towards the negative terminal. It occurs quickly at first as there's lots of charge on the plate, so lots of repulsion, but over time, as charge moves off the plate, there's less repulsion, so the discharging effect lessens. So discharging slows with respect to time. Now we can also measure the rate of discharge by measuring the potential difference across the capacitor. Now it's also the same for the positive charged plate, except this time the electrons stream onto that positively charged plate. The effect is quick at first, but over time, as more electrons move onto the plate, the effect lessens. So discharging slows with respect to time, and the electron movement is now towards the negative terminal. It is in the opposite direction to the electron movement during charging. Now it's important to note that when a capacitor is fully discharged, there's no charge on the plate, there's no difference in potential, the potential difference is zero. So what we can actually do is, let's now consider our charging effect, and we've got our multimeter measuring our potential difference across the capacitor to look at how the rate of charging occurs. So when you plot the measurements of the potential difference across the capacitor with time taken to charge, you get the following graph. So the potential difference increases exponentially when the charge is being charged. It's because since the potential difference is proportional to charge, as the charge builds up, so does potential difference, and as the maximum value of PD is reached, it's equal to the terminal PD of the battery. When the capacitor reaches maximum potential difference, we refer to this is V0. Now this process is an example of exponential decay because the rate of change decreases with respect to time. Now it's important to know the maximum potential difference reached is the EMF of the power supply, which is V0, and it's the same idea for Q, because Q is directly proportional to potential difference. You reach a maximum charge, but it's also an idea of exponential decay, and we call the maximum charge reached in the charging process Q0. Now, its exponential pattern is also true for measuring current in the circuit, but the current we're measuring is in the circuit, not of the capacitor, which is why it appears to decrease, okay, because there's less current in the circuit to be measured. Now, when the ammeter in the circuit reaches 0, you know your capacitor is fully charged. Now, in reality, this is a better measure of knowing when a capacitor is charged, since the capacitor will never get the EMF of the power supply, as it has a potential difference due to internal resistance which prevents it from reaching its EMF. Now again, this process is exponential decay. The rate of change decreases with time, but our I0 is our maximum value, so in this instance it's the start of the charging process. Now we can look at this in terms of equations. So our equation for charging up is going to be V equals V0 times by 1 minus e to the power minus t over RC. Now remember, e is Euler's number and represents exponential change. Now again, this equation is very, very important as it's got a negative power in there because it's an exponential decay. Now you can look at your equation for charge being Q equals Q0 e to the times by 1 minus e to the minus t over RC, and current is I equals I0 e to the minus t over RC. Now remember, the current found in the equation refers to the current in the circuit, not the capacitor, which is why the graph and the equations do not look the same as Q and V. Now again, if we now look at discharging, discharging occurs when the power pack is switched off. So the capacitor discharges discharges is charged through the resistor in the circuit. So again, what happens is, to start our discharging process, you remove the EMF from the circuit and close the switch to complete the circuit. Now again, this is an example of exponential decay. Our maximum value V0 is at the start of the discharging process. Now the discharging process happens the fastest with the greatest potential difference across the plates, so it's when the potential difference across the resistance is the smallest, because the circuit is a potential divider. Now it's important that placing a voltmeter across the capacitor decreases the resistance of the circuit, because a voltmeter has a high resistance but is placed in parallel in the circuit, so this means it will increase the rate of discharge and charge in a circuit compared to expected values. Now if we look at the current graph, it's actually the same discharge curve as if it was current being measured. Again, I0 is the largest possible value measured and occurs at the start of the discharging process. Now this occurs because at the start there's a great number of electrons on the negative plate which then leave the capacitor given a high current, but over time no more electrons move in the circuit, the current drops to zero. It's again an example of exponential decay, and we've got the same idea for Q0 here, the charge falling initially and then slows, eventually reaching zero when all the charge has left the plates. So now our equations for discharge are as follows. For potential difference, V equals V0 e to the minus t over RC, where V0 is the maximum possible value in the circuit. You've got Q equals Q0 e to the minus t over RC, where again Q0 is our maximum value of charge stored by the capacitor, not by the circuit, and I equals I0 e to the minus t over RC. Now you've got to be able to rearrange these types of equations. So as you can see on the screen, to get a value from your exponential, so minus t or RC, what you've got to do is take the natural log of both sides, rearrange to make your subjects, and you can work it through. Now it's important to note the opposite mathematical term of E is natural log, so natural log and E cancel out, with the power of E becoming a normal term in the equation. So log E to the minus 5x becomes minus 5x. Log E to the power of 2 becomes 2. So log E to the power minus t over RC becomes minus t over RC, and you can do this for Q, I or V. So what you'd have to do is, if you wanted to work out a particular value, you would have to take natural logs of both sides. That removes the E and brings your power term down to a normal term. Rearrange to work out your value and you can find your answer correctly. Now capacitors charge and discharge exponentially, so this means their charge falls away and gains in a similar way to radioactive decay. Now in radioactivity you have half-life, in capacitance you have time constant. So the capacitance time constant is constant throughout. It's a constant of an exponential, but it's the time taken to fall by 63%. So our capacitor discharge is very similar to our radioactive decay. However, what we can do is we can actually consider the time constant. Now if the time of discharge was the time constant, our equation can simplify. Now our time constant is worked out by the equation. Time constant is equal to the resistance of the circuit times by the capacitance of the circuit. So it will be equal to Q equals Q0 e to the minus t over t. So we e to the minus 1. So we can write that as the following, or we can link it in like that. So therefore we know as E is equal to 2.718, 1 over E is equal to 0.37. So it means that in one time constant, the value of charge or potential difference or current falls to 37% of the value it had at the start of the time constant, or it loses 63%. Now it's important to note this is a fixed value and is unchanging for a discharging capacitor. Now this is the same principle for potential difference in current. So you can derive the time constant via graphical methods. So on a discharging curve, what you would do is you'd work out the time taken for the value to drop to 37% of its initial value. So you find V0, I0, Q0 from the graph, and then calculate 37% of that value. Now remember, it's 37% of the starting value. So in one time constant it goes from 100% to 37%. In the second time constant it goes from 37% to 14%, because 37% of 37% is 14%, and then from 14% to 5% in the next time constant. Now let's just look at where we get this idea from, because if we know that one time constant T equals RC, so therefore Q equals Q0 e to the minus 1, e to the minus 1 is 0.37, showing that particular idea there. Now we can also carry out the following. We can collate our terms and make RC the subject, and what this tells us is if we plot a log linear graph to find the time constant, if you plotted log Q against T, or log V against T, or log I against T, you will get a straight line graph because it's an exponential, and the gradient of this straight line will be minus 1 over RC, or minus 1 over time constant, whilst our y-intercept will be log Q0 or log I0 or log V0. So you can derive the time constant from a graphical method by doing a natural log against time graph, and our gradient is going to be minus 1 over time constant. So the time constant is minus 1 over the gradient of a log I t graph or log V t graph or a log Q t graph. Now this is a more accurate method of deriving the time constant, as it's easy to take the gradient of a straight line as opposed to taking values off a curving line. So there's less random error in deriving the straight line gradient than extrapolating values off a curving line. But also remember, the y-intercept is either log V0, log I0 or log Q0, so you can then use this to work out V0, I0 or Q0. Now we can also rearrange the equation to find the time taken for the capacitor, so the charge or potential difference to half in a capacitor. So if we know Q equals a half Q0 because it's the time taken for Q0 to half, we sub that into our equations, we calculate our Q0, we do natural log to remove the exponential term, and we get our answer to be log 2 times by RC equals T, and log 2 is equal to 0.69, so the time taken to half is equal to 0.69 times by RC, and this is the same time it takes for the potential difference across the plate and the current in the circuit to half. Now finally, the energy stored by a capacitor. So the molecules of a dielectric are affected by a uniform electrical field as they become charged and become electrical potential energy stores. So on each plate, the electrons or lack of electrons are held on the plate, overcoming their own repulsion. This is provided by the terminal but requires energy supplied by the power source and is stored as electrical potential energy for as long as the charges are held. So when the charges are released, the electrical potential energy is released. So let's have a look at how this works. So you've got your electrical potential energy stores, which we can look at to power our devices. So how can you calculate it? Well, if we know C equals Q over V from the start of this revision session, when we plot V against Q, we should have a direct proportionality, so it's a straight line through the origin. So what happens is, as charge builds up on the plates of the capacitor, the electrical energy is stored by the capacitor. It becomes a store of potential electrical energy. So this electrical potential energy stored is the work done to move the extra charge onto the plates and occurs against the potential difference across the plates. So this stores energy because of this charge imbalance, and so this indicates to us that as we increase our potential we increase our charge, we increase our potential difference, and this requires energy to be done. So the work done is the area under the curve due to an increase in the potential difference in charge in the capacitor. So we can derive an equation from this. So what we know is the area under our curve is equal to the energy stored by the capacitor. So it's equal to a half QV, as it's a triangle under this straight line. So as we see here, as you can form your area under your curve, you can split this into little small strips, or you can just work out the overall shape, and our overall shape is a triangle, so we know it's a half base times by height, so it's a half QV. So there's our equation. So this is due to the area under the graph forming a triangular shape. You can substitute previous capacitance equations into the equations to get the following formulae. E equals a half CV squared and E equals a half Q squared over C. Now these equations are found in your examination book, and any of these equations can be used to calculate energy stored by a capacitor. Now in these equations, energy will be derived in joules if SI units are used for other terms, and all of these equations are found in your data book for your examination. So let's summarize what we've learned in this revision session. So the definition of capacitance is C over QV. We should know a graphical representation of charging and discharging capacitors through resistors, and corresponding graphs for Q, V and I against time for charging and discharging, interpretations of graphs and areas under graphs where appropriate, the time constant equal to RC. We can calculate time constants from graphical data, and the time to half is 0.69 times by RC. We know the quantitative treatment for a capacitor to discharge and the quantitative treatment for a capacitor to charge, and we also know the interpretation of the area under a graph of charge against potential difference. So E is equal to a half QV or a half CV squared or a half Q squared over C. So I hope you've enjoyed today's revision session looking at capacitance for AQA A-level physics. Thank you very much for listening and have a lovely day.